The summer of 1942. British tank crews in the Western Desert were dying inside their own vehicles. Not from enemy shell fire, not from mechanical failure, from engines. The Crusader tank, the backbone of British armored operations in North Africa, was powered by a Nuffield Liberty engine derived from a 1917 American aircraft design. It produced 340 horsepower. The German Panzer IV, by comparison, was producing 300 horsepower, but in a more compact, more reliable package. The Crusader broke down at a rate that appalled its own crews. In some formations, mechanical attrition outnumbered combat losses 3-1. At the same time, 1,200 miles north in a Rolls-Royce facility in Derby, an engine producing more than 1,200 horsepower was being manufactured at a rate of over 400 units per month. It was the Merlin, the engine powering Spitfires, Hurricanes, and Lancasters. One of the most powerful and reliable aero engines in the world, and it was going exclusively to aircraft. The War Office knew what it needed. It needed that engine, or something very close to it. What followed was one of the most consequential acts of industrial improvisation in British military history. An aircraft engine was systematically dismantled, re-engineered and reborn, not for the sky, but for the ground. The supercharger was stripped, the altitude systems were removed. The cooling circuits were redesigned for a steel hull rather than an open fuselage. And the result, designated the Rolls-Royce Meteor, would power British tanks from the Normandy beaches to the Korean peninsula, from the Suez Canal to the Malayan jungle. But the real story of the Rolls-Royce Meteor is not the engineering triumph of converting a fighter engine into a tank power plant. It is the story of how one improvised solution became so successful that Britain never had to find a better one, and what that cost in time, in money, and in steel when the bill finally came due. In the autumn of 1941, the British Army faced a problem it had been postponing for 2 years. The tank engine question, what would power the next generation of British armored vehicles, had never been properly answered. The War Office had issued General Staff Requirement 13 in 1940, calling for a cruiser tank capable of sustained road speeds above 30 miles per hour and cross-country performance sufficient to operate alongside infantry in broken terrain. The requirement named a power output threshold no less than 600 brake horsepower. At the time, no British tank engine in production came close. The firms that might have supplied one were otherwise committed. Rolls-Royce was producing Merlins at capacity for the RAF and Fleet Air Arm. Bristol was supplying radial engines to bomber and maritime patrol programs. Napier was developing the Sabre for the Typhoon. The War Office had in effect allowed the aero engine industry to absorb every engineering resource capable of producing a high-output power plant, and had never built a parallel tank engine industry to match. The consequences were now arriving in the field. Nuffield Mechanizations and Aero Limited, based in Birmingham, had been the primary supplier of tank engines since the mid-1930s. Their Liberty derivative, the Nuffield Liberty, had powered the cruiser Mack A4, the Crusader, and the early Covenanter. It was, by 1941, comprehensively obsolete. The Liberty's origins in a 1917 American aircraft design were not merely an engineering embarrassment, they were a combat liability. The engine required constant maintenance, ran hot in desert conditions, and produced power outputs that left British tank crews consistently outgunned and underprotected against the latest Panzer formations. The man tasked with solving this problem was W.A. Robotham, head of the Rolls-Royce Chassis and Car Division based at Clan Foundry in Belper, Derbyshire. Robotham was not a tank man. He was an automotive engineer who had spent the previous decade developing the Rolls-Royce and Bentley car chassis. But he understood high-displacement engines, cooling systems, and the engineering logic of moving power from one application to another. When the War Office approached Rolls-Royce in late 1941 about the possibility of a tank engine derived from the Merlin, it was Robotham who received the brief, and Robotham who recognized immediately that the conversion was theoretically possible. The competing proposals were limited, and in several cases fanciful. Meadows had proposed a flat 12 engine, the flat 12, that never achieved reliable power outputs above 410 horsepower. Leyland Motors had submitted designs for a diesel power plant that showed promise but was 18 months from production readiness. Neither alternative could meet the 600 brake horsepower threshold within a timescale the War Office considered acceptable. The Rolls-Royce proposal, by contrast, started from an engine already producing more than twice the required output. The engineering task was reduction and adaptation, not invention from scratch. The Merlin that Robotham's team began working from in early 1942 was a 27-liter V12 liquid-cooled engine producing in its contemporary Menck XX form approximately 280 horsepower at altitude. The conversion to a tank engine required the removal of the two-stage supercharger, the system that compressed air at high altitude to maintain power along with the entire altitude management system. The intercooler was deleted. The reduction gearbox was redesigned for direct shaft drive rather than propeller torque. The cooling system was rerouted for a compact armored hull rather than the open airflow of a fighter fuselage. The resulting engine was designated the Rolls-Royce Meteor. The development contract, valued at approximately £150,000 in 1942, roughly £7.5 million in today's terms, was placed with Rolls-Royce in the spring of that year. The first prototype Meteor ran on a test bench at Clan Foundry Belper in the summer of 1942. It produced 550 brake horsepower in initial configuration below target, but demonstrably reliable. The engineering team identified the restriction immediately. Carburation and inlet manifold geometry were carrying over assumptions from the aircraft application. Redesigned for atmospheric pressure operation, the Meteor achieved 600 brake horsepower within 3 months. 4 competing power plant options had been formally assessed by the War Office Tank Board. None of them outside the Meteor were ready. The decision was made. The program had its champion. To understand what the Rolls-Royce Meteor was, it helps to understand what it was not. It was not a diesel engine, the configuration favored by Soviet and German tank designers and later adopted by the British Army itself in subsequent decades. It was not a purpose-built tank power plant designed from first principles for ground combat. It was not compact, it was not light. At approximately 780 kilograms installed, the Meteor was a heavyweight by any armored vehicle standard. What it was in 1942 was available, and what it delivered in power and reliability, and in the hands of crews who had spent 2 years nursing dying Liberty engines across the western desert, was nothing short of transformative. The Meteor in its MK-IVB production form produced a 600 brake horsepower, being the measure of usable power at the engine's output shaft before transmission losses. Later, production marks, progressively refined by the Rolls-Royce team at Belper through 1943 and 1944, raised that figure to 650, then 950 brake horsepower in the Meteor MK-IVA fitted to the Comet tank. A V12 configuration, 12 cylinders arranged in 2 banks of 6 each bank, set at a 60-degree angle. The Meteor retained the Merlin's fundamental architecture, a single-piece aluminium alloy cylinder block. Individual steel cylinder liners, dual overhead camshafts per bank, and a dry sump lubrication system that allowed the engine to operate at angles that would starve a conventional wet sump design. The supercharger was gone. In its place, a pair of SU carburetors, later replaced by a Bendix-Stromberg unit, fed the inlet manifolds directly from atmospheric pressure. The absence of altitude compensation meant the Meteor produced its full rated power at sea level and lost nothing with altitude, a meaningful advantage for a ground vehicle which operates permanently at 0 feet. The cooling system required the most fundamental redesign. The Merlin's radiator configuration, optimized for airflow through a wing radiator matrix at speeds above 300 miles per hour, was entirely unsuitable for a vehicle moving at 35 miles per hour with a closed steel hull. Robotham's team developed a new dual radiator arrangement mounted transversely at the rear of the engine bay, drawing cooling air through louvered hull plates. The system was tested at Clan Foundry through the summer and autumn of 1942 under simulated desert temperature conditions achieved with characteristic British pragmatism by running the engine in an enclosed shed with industrial heaters. The test program was conducted at two locations, the Clan Foundry facility in Belpaire and for Vehicle EA integration trials at Aldershot and the Fighting Vehicles Research and Development Establishment at Chobham. The first Cromwell hull fitted with a Meteor engine chassis registration T11392 completed its initial running trials in the autumn of 1942. 4 prototype vehicle installations were assessed before the first pre-production approval was granted. The primary early failure mode was not in the engine itself, but in the transmission. The Merritt-Brown gearbox, a regenerative steering unit designed to handle the Meteor's torque output, required reinforcement of its final drive housings before it could sustain extended running without failure. What did 600 brake horsepower mean in practice? The Cromwell tank weighed approximately 27 tons. With the Meteor installed, it achieved a road speed of 40 miles per hour, making it at the time of its introduction the fastest cruiser tank in British service. Against the Panzer IV's Maybach HL230 engine, producing 700 metric horsepower, approximately 690 brake horsepower, the Meteor-powered Cromwell was marginally outmatched in raw power, but significantly superior in reliability and maintainability. Rolls-Royce's production standards, applied to an engine derived from one of the most intensively quality-controlled aero engine programs in the world, gave the Meteor a service life that the Liberty engine had never approached. By early 1943, the Leyland Motors facility at Farrington near Preston had been brought in as a second production source. This was a deliberate War Office decision born of hard experience. Single-source production of critical military engines had repeatedly exposed British armoured programs to supply chain collapse. Leyland produced the Meteor under license, applying their own diesel engine manufacturing infrastructure to a petrol power plant. Peak monthly output across both sites reached approximately 450 units by mid-1944. The regional economy that depended on Meteor production by that point extended from the Rolls-Royce Merlin facilities in Derby and Crewe, which shared component supply chains to the Leyland factories in Lancashire. The SU carburettor works in Birmingham and the Meadows gearbox facilities in Wolverhampton. The Meteor was not simply an engine, it was a production network spanning 3 counties. The decision was irreversible. The Meteor had become the heartbeat of British armoured power. What remained was to send it to war. By the 6th of June 1944, the Rolls-Royce Meteor was in production at a rate sufficient to equip every Cromwell-armed regiment in the British Second Army. The numbers were these: by D-Day approximately 1:70. Cromwell tanks had been built, the majority fitted with the Meteor Mk-IV-B. They equipped 4 armoured regiments in the initial assault force, including the 7th Armoured Division, the Desert Rats, veterans of North Africa, now crossing the Channel with an engine that bore no resemblance to the Liberty engine machines that had broken down in Libya. The 11th Armoured Division, equipped with a mixture of Cromwells and the Sherman, deployed Meteor engine vehicles in the advance through Normandy. The Guards Armoured Division used Cromwells in the reconnaissance and command tank role throughout the campaign from August 1944 to May 1945. The operational record in Northwest Europe was unambiguous. On one point, the Meteor engine did not fail its crews. Mechanical breakdowns attributable to engine failure were a fraction of those recorded for earlier British tank engines in comparable operational tempos. The Royal Electrical and Mechanical Engineers, REME, the Army's maintenance corps, reported that Meteor engine change times in the field averaged approximately 4 hours for a trained crew with standard tools. A Liberty engine change, by contrast, had routinely consumed the better part of a working day. This was not a marginal improvement. In armoured warfare, 4 hours is the difference between a tank returning to action before nightfall and a tank sitting immobile on a contested road. The Cromwell's principal limitation in Normandy was not its engine. It was its gun. The Ordnance QF-75mm, the Cromwell's primary armament, could not penetrate the frontal armor of the Panther or Tiger at standard combat ranges. The Comet, the Cromwell's successor, was designed to address exactly this deficiency. Armed with the 77mm HV gun, a development of the 17-pounder anti-tank weapon, and fitted with the Meteor MKIVA producing 950 brake horsepower. The Comet entered service with the 11th Armored Division in November 1944. It was faster than the Cromwell, better armed and powered by the most capable version of the Meteor yet produced. The Comet reached the Rhine in the spring of 1945. The 3rd Royal Tank Regiment was the first unit to cross the Rhine in Comet tanks on the 25th of March 1945. The crossing was made at speed, the Meteor's power output giving crews the ability to accelerate through exposed crossing points that a slower vehicle would have had to approach more cautiously. Then came Korea. When North Korean forces crossed the 38th parallel in June 1950, the Centurion tank was in British service. The early Centurion marks the Mk1 and Mk2 had been trialed with the Meteor engine. The Centurion Mk3, which deployed to Korea with the 8th King's Royal Irish Hussars in November 1950, was powered by the Rolls-Royce Meteor Mky4B, producing 650 brake horsepower. It was the first time a Meteor engine vehicle had fought in a sustained ground campaign against a modern enemy using Soviet-supplied armor. The performance was definitive. On the 4th of January, 1951, Centurions of the 8th Hussars engaged T-3485 tanks near the Imjin River. The T-34, the tank that had broken the Wehrmacht on the Eastern Front, was outmatched. The Centurion's 20-pounder gun and its Meteor-powered mobility gave British crews a decisive edge in engagements fought across the frozen Korean hills. Confirmed kills from the Imjin engagements attributed to Centurion tanks numbered in the dozens across the winter campaign. Not a single Centurion was lost to enemy tank fire in the same period. Korea confirmed what the Normandy campaign had suggested: the Meteor was not simply adequate, it was good. Reliably, consistently, predictably good in cold and heat, in mud, and in combat. The export record expanded accordingly. The Centurion Meteor, powered in its principal combat variants, was sold to 20 nations across 3 decades. Australia committed to the Centurion for its armored corps in 1951 and deployed them in Vietnam between 1968 and 1971, where the jungle terrain placed extraordinary demands on both the engine and transmission. The Centurions of the 1st Armoured Regiment, Royal Australian Armoured Corps, operated in temperatures and humidity that no British test program had anticipated. The Meteor engines maintained by RAME, the Royal Australian Electrical and Mechanical Engineers, continued to perform within specification. Canada acquired Centurions for the Royal Canadian Armoured Corps, deploying them with NATO forces in West Germany through the 1950s and 1960s. Denmark, the Netherlands, Sweden, Switzerland, South Africa, Israel, Jordan, Kuwait, and India all operated Centurion variants powered by Meteor derivatives. The Israeli Defense Forces used Centurions, locally designated Shot, meaning whip, in the 1967 Six-Day War and the 1973 Yom Kippur War, by which point the vehicles had been substantially modified, their Meteor engines eventually replaced by American Continental AVDS 1790 diesels for logistical standardization. But the original Meteor-powered Centurions fought in 1967 in the Sinai and on the Golan Heights, 25 years after Robotham's team had first run the prototype on a test bench in Belper. At peak production, the combined Rolls-Royce and Leyland output of Meteor engines exceeded 4,800 units. The factories at Farrington employed over 2,000 workers on Meteor-related production at their wartime peak. The Derby facility's component supply lines sustained employment across the East Midlands that would persist in diminished form into the 1960s. The Rolls-Royce engineering team at Belper, under Robotham's continued direction, produced a succession of Meteor development variants: the Meteor Mk2 to the Mk3 with revised carburation, the Mkiva at 950 brake horsepower, the Mkivb at 650 brake horsepower as the standard Centurion fit, and ultimately the Meteorite, a reduced displacement derivative, producing 510 brake horsepower for lighter armored vehicles. The engine family demonstrated a developmental range and durability that few military power plants of any era have matched. But the Treasury had begun asking questions. And, inside the Royal Armoured Corps, a different kind of conversation was beginning, one about what came after the Meteor and whether Britain had the industrial will to build it. The Meteor did not die on a battlefield. It died in a procurement gap that Britain spent 2 decades pretending did not exist. The warning arrived early. In 1949, the Fighting Vehicles Research and Development Establishment at Chobham completed an assessment of future tank engine requirements for the next generation of British armoured vehicles, the program that would eventually produce the Chieftain. The assessment was unambiguous. A new power plant was required. The Meteor, for all its operational reliability, was a petrol engine in a world increasingly committed to diesel. It was heavy. Its fuel consumption at operational tempos imposed a logistics burden on armored formations that diesel-powered contemporaries, including the Soviet T-54 introduced in 1947 with a V-54 diesel producing 520 metric horsepower, did not face to the same degree. Petrol is flammable. Diesel is less so. This was not an abstract engineering consideration. In Korea, in Normandy, in every theater where Meteor-powered vehicles had fought the risk of fuel ignition following penetrating hits had been a known and documented hazard. The Soviet Army had drawn the same conclusion from the Eastern Front and committed entirely to diesel propulsion. The British Army had not. The Public Accounts Committee raised the tank engine question in its 1952 report on fighting vehicle procurement. The report noted with a careful understatement that characterized PAC language on politically sensitive matters that no funded program existed to develop a successor to the Meteor for future armored vehicles. The War Office response acknowledged the gap and indicated that assessment work was ongoing. It was ongoing for the better part of a decade. The engine selected to replace the Meteor in the Chieftain tank, Britain's main battle tank of the 1960s and 1970s, was the Leyland L60. A 2-stroke opposed piston diesel, the L60 was an ambitious design that offered high power density in a compact package. It produced 700 brake horsepower in initial specification, more than the standard Centurion Meteor, fit in a significantly smaller envelope. On paper, it was the answer to every criticism leveled at the Meteor. In practice, it was a disaster. The L60's development history is one of the most extensively documented procurement failures in British armoured vehicle history. The engine entered service in the Chieftain Mk-1 in 1966. Within months, reliability problems were apparent. The opposed piston configuration, in which 2 pistons share a single cylinder moving toward each other to compress the charge, placed extraordinary demands on cylinder liner sealing. Coolant leaks, liner cracking, and power shortfalls plagued the L60 throughout its service life. The Chieftain's nominal 700 brake horsepower was rarely achieved in field conditions. Effective output in operational use was frequently measured at 550 brake horsepower or below, less than the Meteor Mk-IVA had produced in 1944. The National Audit Office assessment of Chieftain engine reliability, conducted in the early 1970s, documented availability rates that fell consistently below the Army's operational requirement. In exercises on NATO's Central Front, Chieftains broke down at rates that alarmed commanders. The Bundeswehr, operating Leopard 1 tanks powered by a reliable German diesel, watched their British NATO partners struggle with an engine that had never been made to work properly. The formal withdrawal of the Meteor from British Army frontline service occurred in stages through the late 1950s and early 1960s as Centurion regiments converted to the Chieftain. The last Meteor-powered Centurions in British service were retired by approximately 1964. In export service, the engine persisted considerably longer. Australian Centurions in Vietnam carried Meteor engines until 1971, and South African Centurions, locally modified, retained Meteor derivative power plants into the 1980s. The assessment is stark. The Meteor had been so reliable, so adequate for so long that the institutional pressure to replace it was never sufficient to drive a properly funded successor program through the War Office and the Treasury simultaneously. When the replacement finally came, it was rushed, undertested, and operationally deficient. The development contract for the L60 had been placed without adequate prototype testing. The production commitment had been made before the reliability problems were fully characterized. The PAC noted in its 1968 report on Chieftain procurement that the decision timeline had compressed the test program to a degree inconsistent with the complexity of the engine design. The Meteor had solved a problem, The solution had become a dependency. The dependency had become a delay. The delay had become a failure. Britain's armored corps paid for it in reduced operational availability through the 1970s. The chieftain, underpowered, unreliable, on the central front. The engine that followed the Meteor was not British at all. The Challenger 1, which entered service in 1983, was powered by the Rolls-Royce CV12, a diesel derived in part from the same Condor marine engine family. Reliable, powerful, but emphatically not the purpose-built diesel tank engine that the 1949 FVRDE assessment had called for. Britain had arrived at a capable tank engine by a route that took 34 years and one operational disaster to complete. The Rolls-Royce Meteor powered British tanks for more than 20 years of active service. Its derivatives powered the armored vehicles of 20 nations across 4 decades. It fought in Normandy and Korea, at Suez and in the Sinai. It outlasted the aircraft it was derived from. It outlasted the threat it was designed to defeat. And it outlasted by some margin the industrial confidence that had produced it. The technological legacy is specific and traceable. The Meteor established Rolls-Royce as a credible manufacturer of military vehicle power plants, a reputation the company had not previously held and would subsequently leverage into the CV12 diesel program that powers the Challenger 2 to this day. The engineering knowledge accumulated by Robotham's team at Clan Foundry in cooling system design and high-displacement V12 architecture in the management of torque outputs through regenerative transmission systems fed directly into the post-war Rolls-Royce tank engine research program. It was not wasted. It was absorbed. The Centurion tank, which the Meteor powered through its most important operational decades, became the most widely exported British tank in history. More than 400 Centurions were built at the Royal Ordnance Factory at Leeds and by Leyland Motors at Farrington. They served in conflicts on 4 continents. The Centurion's reputation for protection, for gun accuracy, for mechanical durability, rested substantially on the Meteor's proven reliability. A less dependable engine in the same hull would have produced a different export record and a different chapter in British defence industry history. The human footnote belongs to W.A. Robotham himself. After the war, having overseen the Meteor program from first prototype to full production, Robotham returned to the Rolls-Royce Automotive Division. He wrote in his 1970 memoir Silver Ghosts and Silver Dawn, a candid account of the Meteor's development, including his frustration at the War Office's early skepticism about an aero engine conversion, and his conviction that the project had succeeded despite rather than because of the procurement process that surrounded it. He retired from Rolls-Royce in 1956. He died in 1989, having lived long enough to see the chieftain's engine problems confirm every concern he had raised about the dangers of abandoning a reliable power plant without a tested successor in place. The honest verdict, as procurement historians have consistently recorded it, is complex. The Meteor was an improvisation that became an institution. It filled a gap that the War Office had created through a decade of neglect, and it filled that gap so effectively that the War Office never felt sufficient urgency to close it properly. The 1949 FVRD report had been right. The PAC had been right. The National Audit Office had been right. A purpose-built diesel successor, properly funded and properly tested in the early 1950s, would have given the chieftain a reliable engine and spared the Royal Armoured Corps 15 years of operational frustration on the Central Front. Instead, Britain got the Meteor for longer than it needed it in the L-60 before it was ready. That is not the Meteor's failure. That is the failure of the institutions that surrounded it. The War Office, the Treasury, and the procurement committees that chose the comfort of a working engine over the discomfort of developing its replacement. The Meteor deserved a better successor. The men who crewed the tanks that carried it deserved a better answer to what came next. If you found this history valuable, give the video like it's the single best signal you can send this channel. And if you want more stories about the aircraft, ships, and decisions that shaped British military power, subscribe to UK Defence Archive. We'll see you in the next one. Somewhere in the Tank Museum at Bovington, a Cromwell sits on a concrete floor, its Meteor engine long since drained and cold. 40 horsepower per litre, 12 cylinders, 2 banks of 6. Stripped of its supercharger and sent to fight in the mud rather than the sky, the engine that powered Spitfires reborn in steel and urgency to carry British armor across the Rhine.